Hello, everyone. Maybe let's just wait for a few seconds to see the number of participants increase and as they are, let's say, released into the webinar. And we'll start in just a few seconds. Okay. Good morning, good afternoon, and good evening, ladies and gentlemen. Welcome to today's webinar, where we are going to talk on how you can optimize your AI model and what are some of the aspects that you have to consider for your prototype for the OrbitalAI challenge as part of the AI for your challenges. So I hope you are as excited as we are, because we have plenty of amazing speakers from top European companies that are working, let's say, arduously in this domain right now and are developing the latest technologies that we are going to see revolutionizing the Earth observation industry and, let's say, also the AI industry. So without further ado, I'm just going to run through a few practicalities on today's webinar. So in case you have any kind of question, please use the Q&A function that you have and ask your question over there. Depending on the time that we'll have, maybe we'll answer some of the questions that you have already after the presenter finishes their presentation. And if not, we are going to keep that question for the Q&A session that we have scheduled after 6 o'clock. So this only lets me to go a little bit through the agenda of today's webinar. So as you know, for the OrbitalAI challenge, we have two tracks. One which concentrates on the FISAT-2 mission, and then another one that concentrates on the ImagineE mission. So that's why you'll see that some of the presentations will be more focused in the first part. The first presentations are going to be more focused on the FISAT-2 mission. However, I'm sure that some of the insights or information that the speakers are going to share with you can be applied to both tracks, obviously. And then the next part is going to concentrate more on the ImagineE, so the hyperspectral camera that is going to be mounted outside of the ISS. So let's go in the first part of our webinar, as we said, for the FISAT-2 mission. And it's my pleasure to introduce you to our first speaker for today and for the first slot, which is going to concentrate on the onboarding of AI applications for innovative EO techniques. And here we have Alessandro from CGI. He's a director and scientific coordinator at CGI. And then we have also Georgia, and she's working at GeoK, and she's an environmental engineer over there. So Alessandro and Georgia, the floor is yours.
Thank you, Janot.
Thank you.
Okay, let me share my screen. Can you see my screen in the presentation mode?
Yes.
Okay, good. So hello, everyone. Thank you for joining this webinar. I'm really happy to share the opportunity to talk with all of you together with Georgia. My name is Alessandro Marina. I'm a CGI director, and I'm acting as a scientific coordinator of the FISAT-2 mission. And the title of this presentation is Onboard AI Apps for Innovative Earth Observation Techniques. Georgia, would you like to introduce yourself?
Yeah, hello everyone. I am Giorgia Guerrisi from GeoK, and I am an Earth observation application specialist.
Thank you. So we are going in tandem in this presentation, and I know we have really little time, but we will try together to touch some key elements. So the first thing when we were designing this mission was that we wanted to build a game-changing Earth observation CubeSat platform running AI application in space which were developed by its own user and deployed on the space, but operated from the ground. And when we were designing this mission, actually, we had two main objectives in mind. The ability to perform the innovative mission proposed, so innovation, new Earth observation techniques, and the demonstration of the disruptive advantage that the onboarding AI brings to the mission. We, every time that we were thinking about the scope of the mission and how this can be, which type of achievement this mission can reach, we have to think about an analogy and why onboarding data processing. And if you think about when the first car were built or were used, there were not actually the real need of new cars. They were slower than horses, or they were having a lot of pollution. But on the other side, no one who was building car at the time could think that car now can be automated, rugged, and we can live in a world where we really use this commodity to move around the world. So what we had to build was to have a vision of what the AI capability in space can brought into the future. Georgia, would you like to?
Yeah, sure. And yeah, so in this sense, the innovation in the context of onboard data processing is represented by moving data processing from Earth to space. And this because remote sensing is developing so fast that data are becoming increasingly diverse, and also the amount of available data is increasing at a very fast pace. And these poses new challenges that are mainly represented by developing new efficient processing procedures that are able to support the emerging Earth observation applications. And the main challenge in the main advantage in onboard data processing is represented by two main points that are reducing the time to receive the information, because we can extract directly on board the information instead of the raw data, and also limit bandwidth usage, because we can, for example, send to the ground compressed data or only the information which are lower in terms of amount of data compared to the original data. However, we have to take into account that the resources available on board are not comparable to those on the ground. And so this means that onboard processing require an appropriate combination of software and hardware solutions. And for this reason, artificial intelligence models must be flexible, robust, and must require low computation burden.
That's why, in the light of this, we have designed a set of default AI application which will run together with the overall mission. Just for your information, also, we have also designed this application trying to cover different machine learning approach, from the supervised to the unsupervised. In particular, there will be two applications which will cover the supervised approach, which are related to cloud detection and autonomous vessel awareness, which covers problems like image segmentation and object detection, respectively. And there are two other applications, one which is related to the encoders, the deep image compression, and one which is related to the image segmentation set for the generative adversarial model. In particular, going in the details, so one of the application is the set-to-map. The set-to-map application aims to, through the generative adversarial network, to transform a satellite image in the map of streets. And I mean, the way how this type of application can be seen as innovative is if it is driven by an emergency scenario. So when there is actually the need of transporting information directly on the ground. So what we had to do in terms of challenging related to this application was to actually make sure that by the time when the acquisition was taken, till the time to the information could be delivered to an agent on the ground who was maybe facing a flood. And we in Italy in those days can actually know how this dynamic can be. Even if the sense, so we tested this in also in Pakistan the 1 year ago to see whether, because the conditions were also problematic there, but also with the optical sensor. But again, what we did was to push the limit of the hardware and the and on the time processing in order to provide this information on the ground. The other application, as I mentioned before, is the cloud detection. As you know, the cloud detection, it's something like a best practice when you need to extract information with an optical sensor. But the things which was absolutely new in this, I would say, in this mission, was that this application can work as a service for the other application. So basically, in the same way, your application on the phone can connect to another application, and you can send email from your, you can send file in your email or in your WhatsApp via another drive, external drive. In the same way, this application can tell us which are the cloud-free patches which can be processed by another application to reduce the computing time. Georgia, will you go next?
Yeah, and then we have the high compression hub that exploit deep autoencoders for image compression on board and reconstruction on the ground. So this means that we can compress the acquisition by the encoder part of the network and send them to bandwidth for data transmission. And the performance of this application are evaluated in terms of image similarity, but also in terms of how the reconstructed image can be exploited by other applications, for example, for object recognition. And we have then the autonomous vessel awareness app, and in this case this application exploits deep learning to detect and classify vessels, and the main point related to this application is that it can demonstrate how information that are generated in space can be exploited for mission operation. And so, for example, in a satellite constellation, to identify areas for the next acquisitions.
And the last item is that our mission is open to all application. And we really look forward to have all new ideas and application which can prove how AI application working in space can open to new future scenario. And before closing, I would like, of course, to thank all the partners that we are working with. Starting from the Prime, Open Cosmos, to all the application developers, SIA, KP Labs, and JK, and Simera Group and Robotica, which are working on the component side. And it's really a pleasure to have this mission together. It's challenging, but I would say, I think we managed to be in the 10 minutes. So also that challenge was covered, you know.
Thank you very much, Alessandro. Indeed, so many challenges trying to present such a complex project in such a short time. But I guess we should offer the participants, let's say, a few insights or a few flavors on what this, let's say, humongous project presumes, and then we are waiting for their questions for the Q&A, and then also if they have more extensive topics, they can reach out to us. So once again, thank you very much, Alessandro and Georgia. Now I want to go to our next speaker, whom is going to be Fintan Buckley, and he is the CEO of Robotica, and he will shed some light on the limitation and challenges of onboard data processing. So let's give a warm welcome to Fintan.
Yeah, Alessandro, I think you need to stop sharing so I can share. Okay. There we go. Okay, so just going to talk briefly the architecture on board the satellite in which the applications operate, and then touch briefly on some of the challenges that we have encountered when taking applications that have been developed within the standard training frameworks, PyTorch, TensorFlow, and mapping those into the operational environment for the satellite. Okay, so the architecture for PSAT-2 is for the payload. We have an 8-channel multispectral camera developed by Samara. We have the Cognizant AI processing platform being supplied by Robotica, and then as well as standard functionality for operating the satellite. We also have the Enema Framework, which is the environment in which the applications operate. So to then briefly describe on the Enema Framework, as Alessandro touched on, it's a series of services that are made available to the applications. The framework itself does the orchestration, schedules the running of the applications, and the interleaving or the multitasking of the applications. And the environment, the framework, allows the scheduling of the capturing of images from the camera system. You also have access to the orchestration or the positioning attitude of the satellite itself, and to the location information. And then we have 3 services that are used to manage the processing of the AI image itself. The images that come off the camera, as I said, are multispectral. There's 8 channels, and they are quite large images. So because this is an edge processing environment, and there are compute limitations, the application, the image will be required to be segmented into tiles before being applied to the AI processor for inferencing. And then there's the ability, depending on the application, to actually reconstruct output tiles or reconstruct output images from tiles if that's required. The environment that we have is a highly configurable environment, and the approach that we've taken is to have services which will be driven from JSON files, which the applications can construct on the fly, or they can be static, and they will be used to configure the operation of the tiler, the AI service itself, and the mosaic. So to go into a little bit more detail, and this is a high-level view, and there are steps that are emitted from this. But essentially, what comes in off the sensor is it's 8 channels, and it's in a 12-bit packed format. So what that means is that each pixel is represented by 12 bits, but the bits are packed so that within 24 bits you will have two pixel values, if you like. Okay, so minimizing the amount of data that needs to get transferred from the instrument itself. And so the tiler will take this sensor data, extract the particular channels that are of interest, and construct tiles that are in a format that the model that's going to use to process the tiles will accept. Okay. For the AI processing itself, we have the neural network model, which is represented as a software model. That is loaded onto the processor. There are also filters which can be used for some of the standard pre-processing and post-processing operations, such as mean and scale and what have you, to further prepare the input tiles for processing by the AI processor. And finally, when the output tiles are available, the mosaicer can be invoked as well to reconstruct an output composite image, if you like. So typically, you'll do this if you're doing a segmentation type application, such as the SAT2MAP that Alessandra referred to earlier, but probably if you're doing an object detection, you most likely don't need to do that. Okay, so we also have the ability at each stage between the tiler and the AI processing to inject application-specific processing on the tiles if that is so required. Okay, so this is kind of giving you a flavor of the configuration or the flexibility, if you like, of the system. So the configuration is broken up into configuration of the tiler, of the mosaicer, of the neural network or AI processing itself, and then for system level configuration as well. So starting on the top left, the tiling, what you're doing is you're configuring the size of the output tiles. We have the ability to overlap tiles. So when you're doing object detection, such as for the ship detection, you can define a degree of overlap so that you are guaranteed that any object that you're trying to detect will be fully captured within a tile, rather than having a ship, for example, that so happens to expand over two tiles and may not be detected. You can also specify which bands you're interested in. It might not just be an RGB, but it might be some of the NIR bands that are going to be processed by the AI model. Everything works on folders in the mass memory. So down on the bottom here, where you're specifying the folders where the input images are located, where the tiles are put, where the neural network models are. And during the validation stage, we have the ability to actually self-verify, where we can determine that the inference results are actually matching against expected results. And then over on the right-hand side, what we have here is the configuration of the neural network model that will be used for the application. We have the ability to chain operations so that for applications which have a requirement to, let's say, doing an object detection and then doing some further degree of AI analysis on objects that are detected, that can all be handled on the AI processor itself by through chaining the operation on the device itself. And then these PCDs are what we use to configure up the image pre-processing operations that would be run on each tile before inferencing is performed. Okay, so in terms of limits and challenges, a couple of things that need to be borne in mind. First of all, that the neural network models can be large, and we do have limitations in terms of the size of these models. The absolute maximum we can accommodate as a model. After it's been processed and compiled to run on the accelerator, the very, very maximum is around 220 to 230 megabytes in size. But we would kind of recommend, when selecting a model architecture, to be looking at something that is more in the 100 megabyte range where possible. Because there's limitations on the mass storage on the OBT itself. The bigger the model, the bigger the risk of having bit upsets at any stage during the processing. And if there's a requirement to update or to change or to upload new versions of the model, as well as the space asset that is in flight, the bigger the model, the more time that takes, and the more costly it is to actually get that new version of the model up there. But there is the ability to do that, to actually to update the models over time. Okay, the key thing and the challenge that we have been addressing and focusing on throughout the PSAT 2 program so far is actually, how do you map the processing that's done in the training framework to what is actually going to happen on the satellite. Okay, and the key challenge is actually understanding what the training framework is doing. Not a lot of the training that happens is the data scientists will start off with pre-trained models with preset processing functions that are used to prepare image data for inferencing, etc. Okay. A lot of that now is hidden because the training frameworks are getting so sophisticated. All right. But when we go to deploy on the edge, on the space asset, and this applies not only to deploying on satellites, but actually on any edge device, is actually understanding exactly what's happening in the training framework, so that you can actually you can reproduce that processing flow when you go onto the edge device. Okay, so things like what's the image size that's been used to train the network, what's the channel order, etc. The training framework might be using built-in functions. They may not be available on flight. So it's actually understanding, what are these functions doing, and being able to either design them out of the training framework, or else having as part of the pre-processing, making sure that same same processing steps are implemented. So examples of this is, many of the training cycles or the trainings methodologies, that you're using for image data. You'll start off with JPEG models or bitmap models or whatever, so things that are humanly readable. When you go on board satellite, you're not dealing with JPEG models, JPEG images. You're actually dealing with raw pixel data. So actually understanding, so within the training framework, when it uses OpenCV or whatever, what is it actually doing when it opens that model? Is it producing an image that's planar or interleaved in functionality? What's the pixel depth size? Things like that. So it's actually understanding that at a very high level of detail to correctly map the operation that's happening in the training framework onto the edge device. Okay, so this is a sample framework that or a methodology that's used when doing inferencing and training within a training framework such as TensorFlow. So you're starting off with a FITS image, which has a certain file format. You'll load that using NumPy, using Python library. You'll resize the image using OpenCV. You then normalize the image using an OpenCV. You'll do the inference, and then you'll renormalize back. Okay, and then save the image. So this processing flow would then need to be mapped onto what the capabilities are on board the OBC as well as the AI processor itself. Okay, so so key questions are, what's the size of the input and output of the model in terms of the input tensor, output tensor side? What's the shape of it? And what's the pixel layout? Okay, is it RGB? Is it BGR? Is it planar, so that all the red pixels are first and the green pixels and the blue pixels, or is it interleaved? So is it red pixel, green pixel, blue pixel, or whatever? Okay, and then the other thing is the data resolution. Are you training in 8-bit? Are you training in 12-bit? Are you training in FP32 float, etc.? And then how do you map that? Okay, so so this is what when you actually go and do inference on the AI processor, this is a description of, in one particular example, what the input and output looks like. So first of all, you have the size of the model itself. So sorry, the size of the input tensor to the model. Okay, so it's 108 and bytes, so kilobyte, 108 kilobytes, and then your output size of 1400 bytes. Okay, and then the input tensor itself, in this case, is an FP32, and the size, it's a 3-channel 300 by 300 image. And then the output is in an FP16, which is a half precision data format, which is what is the native data format on board the AI processor. And in this case, it's producing an output tensor that's 7 channels with 100 entities per channel. Okay. All right. So in terms of pre-processing, the first thing you got to do is get your image into the right shape. The tiler helps with that, so that before you actually pass it to inference, tiling it down to the 256 by 256, so the 320 by 240 image size as required. Typically, then there's a normalization step that happens where you will either normalize your pixel values to between -1 and +1, or between 0 and 1, and then possibly also doing that using a mean and scale process. Okay, so in Python, this is how it might look like. We will provide filters that will enable that to be done on the AI processor itself, but these mean and scale values need to be known, and sometimes trying to extract that out of the training framework is a little bit of a challenge. Okay. Data conversion. So the image data that comes off the sensor is a 12-bit packed image format. Okay, each pixel is represented by 12 bits. Okay, this is the highest resolution that the imager supports. We provide functionality within the tiler to downscale the resolution if required. So if you have a model that's trained on 8-bit pixels, so we have the ability to generate tiles that have 8-bit pixel resolution. When you do that, though, you are losing information. So when you scale a pixel value, you're manipulating the data that you're working on. Okay, so when you're going from a pixel value that's in the example we're using here is a pixel value of 1500. If your training position is 16-bit and your test data is 12 bits, there is going to be a loss of information that when you go from one to the other and an accuracy. And typically that's represented by having gaps in the histogram when you map it out and do your conversion. So this may have slight impacts in terms of the results of the inferencing that you're getting out of the AI processor on board satellite as against what you see on the training framework itself. Okay, and then finally, on the post-processing side, there may be a requirement to actually reverse, if you like, the normalization process to go back from the scaling between -1 +1 to actually going to pixel values in the range 0 to 65535 or whatever, and then this can actually be done on the AI processor itself. But again, the actual parameters to this unnormalizing, if you like, need to be known and specified so that we can do that on the processor itself. Okay, so that's the highlighting what we want to communicate in terms of, you know, this processing can be done. It's straightforward to do, but the key is to actually understanding what is happening in the training framework before you start to try and map it onto to actually running on the satellite asset itself. Okay,
Thank you.
Thank you.
Thank you very much, Fintan. Indeed, it's very important to understand how the processor works and exactly what the participants should consider when thinking about their AI model. So thank you again very much for your presentation. Now let's move to our next speaker, whom is going to be Jakub Nalepa, and he serves as the head of artificial intelligence at KP Labs. And he will discuss a few tips and tricks on the techniques for optimizing your AI model for onboard data processing. So let's welcome Jakub.
Absolutely, thank you. So, right, I think you should be seeing my screen. And in the already heard from Fintan, what are the challenges concerned with a deep network onboard satellite, or basically onboard any edge device. We know that this cannot be too large because we do have some constraints which are imposed by the hardware. And also Alessandra and Georgia mentioned that we have something which is called cloud detection, which is basically the hello world in satellite image processing, because we can imagine that after capturing the image on board satellite, we might have some areas that are cloudy. In this case, we know that those cloudy areas might not be used as an AI application if we track small objects. So this is a very good chance that for such small objects, the clouds would be too heavy, too large to basically allow the AI algorithm to work on that kind of data. So we could take a decision to perhaps reschedule the capturing process or to handle this kind of image in a different way. Also, what might be of interest is that that kind of cloud detection could be a service to other applications. As Alessandra mentioned, we could use that kind of AI applications input to other applications that are running on board to make sure that we do have good quality data for further processing. Right, so the big constraint is that we are going to execute this kind of deep network or algorithm on board satellites. So you presume that there are some constraints concerning the memory requirements, so the model could not be too large. We have some energy consumption constraints, etc. So a lot of things that come directly from the fact that we are running on board an edge device, which fundamentally is constrained from the hardware point of view. And there are indeed some approaches to have a deep model a bit compressed and a bit more compact for running at the edge device. Basically, it could be deployed at different levels. So we could use a classic neural network of a given architecture, and then we could try to sort of optimize this architecture that is already existing, for instance, using the quantization process for pruning of the network. There are also some a bit smarter techniques for sort of developing the deep network for onboard processing. So if we look at this left-hand side of the slide, we'll see that we could use, for instance, the neural architecture search, where we basically adaptively design the architecture to fit into. So this could be, compact. This could be very small in terms of the memory consumption, or this could be fast in terms of the execution speed. And today I'll show you the example of another approach, which is called the knowledge distillation process, where we could indeed benefit from a large capacity deep network. Deep network that can be trained, and we know that it will generalize well over the unseen data. So the idea is to have basically at least two models. The model which is big is called the teacher model, and this could be a huge model which requires a lot of memory. But on the other hand, we have a student model which is much smaller, it is compact, and our objective is to run this kind of small and compact model on board an edge device. So basically the knowledge distillation process is something which basically allow you to benefit from not only the ground truth data that you could have. For instance, the examples of cloudy images could be an input to a supervised learner, but on top of that, you can benefit from the knowledge that is already learned by the teacher model, which is, let's say, too large for deploying it on board a satellite. Having those two, so we have the architecture that is already working and it is huge, and a smaller model that we know will fit into the target hardware. We could try to learn the model to not only benefit from the ground truth data, but also from this knowledge which is in there in this big model. So this could be, for instance, deployed within the distillation loss, which could be basically a part of the knowledge distillation process. And here's the example of the full pipeline, how we could exploit this approach to build a compact model. We start from the ground truth data. This could be, for instance, in the context of cloud detection, this could be a set of examples showing, for instance, a satellite image together with the ground truth mask showing the areas which are cloudy. Then we prepare a huge model, which is this teacher model that could be memory hungry. Then we train this model and we verify if that works over the unseen test data. So we always keep aside the test data, which is never used during the training process. And then we can have the smaller model that will fit into the target hardware, because we know some constraints that relate to, for instance, memory or the energy consumption that needs to be adhered to basically run this model on board the satellite. Here is the actual, the example on how we could utilize this large capacity learner to have a big and well performing model. So we built upon the Enema Framework, which is very well known in the medical image analysis field. It's been actually used for different tasks that relate to image segmentation in the medical field. So we know that this kind of framework works very well for difficult data. And this framework is built upon the assumption that we sort of automatically build the entire processing chain. So we have the deep model, the pre-processing, and the post-processing as well. So this is fully data-driven, and based on the data that we have, the training data, we could develop the large model that will work for difficult data. But again, it will not fit into the hardware that we have on the edge, especially if we have an ensemble of different models. So this is a very good chance that after running this Enema framework, we would end up having, for instance, 5 big units, which will result in 125 million of parameters, which means that it is a huge model and it will not be very easy to uplink this kind of model to the orbiting satellite. On the one hand, we have the model that works very well. We know that it could segment the image accurately, but on the other hand, it is not useful in practice because it cannot be run or cannot be uplinked to the operating satellite. So to tackle this, we can build a much more compact model, which is again a simple unit architecture, but you can observe that we have a much smaller number of parameters that are trainable. So they affect the size of the model. And we could, in this example, can observe that the reduction in the number of parameters is super huge. We have almost 300 times smaller model, which is our student model that should be trained in a knowledge distillation pipeline from this huge model and from the ground truth data that we also have. So based on this approach, we also always need to verify if the big model and the small model basically work correctly. And this kind of comparison could be both at the image level, so you could just observe in the case of cloud detection if the segmentation maps are correct, given that you have the ground truth data. But what might be more interesting is to verify if the difference in the quality of, for instance, segmentation or classification or any other quality metric that would directly reflect your task is different in a statistically significant manner when we compare a big model and the small model, the compact one, which I think is very important while deploying things at the edge, because we want to make sure that things can work in practice, or we also understand why they might not work for specific cases. So this was actually our standard approach, to have a set of statistical tests to verify if, for instance, this big, huge NN unit model or a set of models delivers the same quality segmentation as our compact model. So you can observe that it is pretty much well defined how to compare two models, because we have the unseen test data, which we always keep aside the training process. Then we just compare the results obtained for every single sample from this test set. And you can observe that if the difference in quality between your huge model and the small model is not statistically significant, you're in a good position, because you know that your compact, small, and efficient model is ready to be deployed on board either VSAT2 or any other edge device. So I would certainly strongly encourage you to also have the statistical analysis of models to better understand when this could work in the target environment and when it may fail, because understanding the failures could be very important for practical applications. I think that's it, and good luck.
Thank you very much, Jakub. Then let's go to our next item for the VSAT2 mission. So it's my pleasure to introduce you to Sofia Oliveira and Nelson Pires from CHEA, and they will talk about the trade-offs between, let's say, accuracy and speed for your AI model. So Sofia and Nelson, the floor is yours.
Yeah, just trying to share our presentation.
Yes. Great, we can see your presentation.
Okay. Okay, right. Thank you very much. So we are going to talk about the trade-offs between the accuracy and speed when building onboard AI models. And the onboard processing for satellite remote sensing images refers to the capability of processing and analyzing the data directly on the satellite itself, without the need to transmit the raw data back to the Earth for processing. This approach offers several advantages, such as the reduced data transmission requirements, real-time analysis for faster decision-making, optimizing the use of available bandwidth and resources, optimization of the satellite platform. The implementation of onboard processing involves the integration of specialized hardware and software on the satellite platform, including high-performance processors, data storage systems, algorithms for image processing and analysis, and real-time decision-making capabilities. Overall, the onboard processing is a growing trend in the field of satellite remote sensing, enabling a more effective use of satellite resources, thus improving the quality of remote sensing data products. When building onboard AI models for satellite applications, there are some trade-offs between accuracy and speed due to the need for low power consumption, low latency, and high performance processing. Here we have some key considerations. So the onboard processing needs to strike a balance between accuracy and speed, considering the available computing power and time constraints for decision making. There's a need to optimize AI algorithms and models to be energy efficient while maintaining an acceptable level of accuracy. It is essential also to balance the latency requirements with the level of accuracy needed, favoring faster processing for time-sensitive and emergency scenarios. AI models need to be optimized to deliver high performance within constraints of onboard processing capabilities. And finally, there's a need to balance the model complexity and size to ensure they fit within the onboard memory and processing constraints while maintaining acceptable accuracy levels. So to address these trade-offs, we can use several techniques such as model compression, quantization, and pruning, which reduce the model size and computation requirements without significantly sacrificing the accuracy. Other way to address these trade-offs is by using hardware accelerators, specially designed for AI tests. Hardware such GPUs, field programmable gate arrays, or vision processing units as the one based for FISAT2 mission. So model optimization techniques and hardware choices play a crucial role in achieving a balance that meets the specific requirements for satellite systems. Now, explaining the model optimization techniques in more detail, the model compression aims to reduce the size of the AI model for removing unnecessary parameters while maintaining the accuracy. One of the most popular approaches is the use of deep neural networks model distillation, which involves a smaller compact model, the student model, to mimic the behavior and the predictions of a larger, more complex model. So the teacher model. The student model can then replace the teacher model while consuming fewer resources. The quantization technique is the one that reduces the precision of numerical values in the AI model. Typically, deep learning models use 32-bit floating point numbers for storing weights and activations. With using quantization techniques, we can convert these high precision values into lower bit precision, such as 8-bit integers. Using this technique, we can reduce the memory footprint and the computation requirements of the model. Since not all weights in a neural network are equally important, pruning methods involves removing unnecessary connections from the neural network to reduce its size and computational requirements. Pruning methods that identify and remove less important weights based on their magnitude or sensitivity to network output. However, careful pruning strategies are necessary to minimize the impact on accuracy. So, overall, by combining all of these techniques, it is possible to achieve substantial model compression and optimization, and the achieved resulting model will be smaller, faster, and more suitable for onboard processing in satellite applications. Now, Sophia, you can continue.
Okay, thank you.
The micro.
Can you hear me?
Yes, maybe just speak a bit more louder, but we can hear you. Now we can't.
Yeah.
Okay, now can you hear me?
Yes, perfect.
Okay, sorry. And you can see the presentation?
Yes, yes, we can.
Okay, so now I will continue and I will talk to you a little bit on the context of the FISAT2 mission, on the techniques that we applied on our application to balance this trade-off. So for the FISAT2, we worked on an application to autonomously detect and classify the vessels on board the satellites. And to develop this application under all of the satellite requirements, we had to balance very well this trade-off between the accuracy and the speed of the model that we are going to use. And for this, we used some of the techniques that were previously presented by my colleague and the previous presentations as well. So first of all, for the detection model that we used the YOLO model, and we opted for a compressed version of the YOLO algorithm, the YOLO Tiny, which is far less complex since it uses fewer convolutional layers and is faster and a smaller model. So in terms of disk space, it's 70% smaller. So we managed to achieve a faster and smaller model. And then we were using the YOLO Tiny version model, and we also converted the models of the applications for the FISAT2 to a more compressed version of the models using OpenVINO. OpenVINO is basically is a toolkit developed by Intel that enables efficient deployment of deep learning models on a variety of architectures, including the VPU. And this model conversion process involves several optimizations such as model quantization, fusion of operations, and hardware-specific optimization. And all of these processes aim to reduce the computational requirements and the memory footprint of the model. And this will allow achieve faster inference speeds and lower power consumption. And here we have just a few results comparing our YOLO Tiny model before and after converting it to the compressed version on OpenVINO. And we can see that we managed to lower the power consumption and the inference speed while maintaining all the performance values. And yeah, overall, these were all the techniques that we applied to manage the trade-off between the accuracy and the speed. And yeah, the 10 minutes are gone. I think that's it. Thank you very much.
Thank you very much, Sophia, and also indeed very interesting how you can downsize the model and still keep the same results. So I think thank you very much for all the speakers that presented up until now for the FISAT2 mission. And now we are going to switch gears and go to the Imagine mission. And it's my pleasure to introduce you to Nicola Milo, who is working at Thales Alenia Space, and specifically dealing with, let's say, AI models that are run on the edge. So without further ado, Nicola, the floor is yours.
Hello, everyone. So yes, I will share my screen. Let's go. Here we are. Is it you can see the slides? That's okay.
Perfect. Yes.
Yeah. So yes, I am Nicola Mailloux, working at Thales Alenia Space on the in the observation and science organization, and I am in charge of, let's say, AI capabilities for different programs. So let's move on the Imagine mission with a few words about AI model optimization. So just as a quick reminder, the importance of onboard AI capabilities is absolutely essential for the future of observation and exploration as well, and because exploration missions are also concerned by all this, and it is very important as well for this area of applications. So there is obviously fast insight generation, which is a key element, and we want good reactivity in plenty of cases. The bandwidth optimization is also a very important aspect. And we, for example, we know that on the SHINE mission, for example, we are actively working on adaptive compression, depending on the presence or not of object of interest or presence or not of cloud images. We foresee a lot of application regarding filtering of the telemetry by removing uninteresting images containing too much cloud, for example, or filtering images containing only some objects of interest. There is also a topic on autonomy, especially if you think about the future of in-orbit servicing on this kind of applications. The autonomy will be very important. I'm not saying that AI will solve everything, but it will be a contributor to this the level of autonomy we will want to reach in that cases. A bit less visible when we design the satellite. We take a lot of attention on onboard anomaly, on their detection and the health monitoring of the system in general. So here, onboard AI capabilities are here to help as well. It's really important on this part, and we are given the amount of power that we have on board, we are able to deploy, let's say, very advanced anomaly detection methods. Last but not least, the security and the threat is, as you know, a huge topic in the current period. We are thinking about the future, about security and threat detection. On here again, AI is here to help. We see a lot of similarity for the future on what is done on the ground with threat detection, intrusion detection, etc. Probably in the coming years, we will see something similar on board. Okay, let's move on to the next slide. Regarding environmental use cases where reactivity is key, and we all have in mind the wildfire, of course, oil spill detection, methane emissions as well, and disaster management in general that requires a lot of reactivity. And when we want to be as efficient as possible on satellites on the eye, can bring a significant contribution into all that. If you think a bit about the future on the edge of rapid revisit with small or not so small constellations that are coming into the picture, onboard AI is also an accelerator in a way. They multiplies the effect of rapid revisit in a way. Okay, next one is about the Imagini mission. As a reminder, yes, Imagini stands for Mounted Accessible Global Imaging Node. So it's really a fantastic testbed to embed applications containing AI or not. And by the way, inside the ISS, it will offer two main sensors: an RGB camera and an hyperspectral camera. So it's really a great opportunity to have two sensors on board and be able to use them, let's say, simultaneously. There will be it's a very good testbed for onboard applications for AI, image processing, and you have to see that as an extension of the Azure cloud solutions. It's very elegant as the software frameworks which offer a really continuity between what you can do on the cloud, on Azure traditionally, and here you can almost do the same about the ISS. So which is it facilitates a lot of things, and we are clearly changing on coming to a new era in terms of software development for onboard applications. Okay, next one. To be a bit more specific about the hardware specifications that will be available on board the Imagini mission computer, we have seen previously a good presentation about all the constraints that onboard processing can have. And here again, it's a fantastic, let's say, opportunity to have so much processing power, but still it's very limited compared to what you have on a traditional cloud infrastructure. It's not, of course, scalable. You have only a certain number of cores. We will have 16 A72 cores. It's an ARM CPU, which is used in plenty of applications, a very popular architecture. It will be clocked at around 2 gigahertz, between 1 and 2 gigahertz, with some possible of adjustment if needed. The memory will be, total memory will be about 32 gigabytes of RAM, and the storage will be of a similar size. So this is amazing numbers for something on board, but still we'll have to be careful about how we use those resources. They will be precious, knowing that we will onboard several applications on Imagini. the key question is how to optimize properly our AI application. And we have seen previously that neural networks in particular can be huge, and they take a lot of memory and sometimes a lot of CPU resources for the inference, and we need to be careful about it. Very important point for the challenge, there will be a guarantee on minimum available resources. It will not be everything at the same time. It will be only a subset of these resources. About 8 gigabytes of memory, 4 cores would be available at minimum at 2 gigahertz, and storage 2 gigabytes. So yeah, those figures are big, but not so big. We need to be a bit careful about what we do, and in terms of application designs, that's important to have that in mind. Okay, it's a different view of what has been said previously, and we have to keep in mind, depending on the application, and we are very, let's say, eager to see the applications that will be proposed. But in some cases, latency will be an absolutely important factor. Memory on CPU usage will be a constraint in any case. Depending on what you do, it will be difficult to have everything at the same time. We will come back to it in a minute, but processing duration and scheduling constraints on this software framework will be something to consider as well. And of course, the raw performance in terms of accuracy, and this has been described already, and the bandwidth capability to process a certain number of pixels per second. And the idea is to be fast enough to offer, let's say, significant and useful applications. And the trade-off between all these will be needed to have, let's say, applications that run smoothly and by creating value. Okay, a few words now about the machine learning optimization techniques. We will provide a bit more detail about the quantization principle. It's actually a broader topic. On the left, there is a reminder on the structure of a neural network. You have the input x1 to xn, the bias b, the weights on the synapses, and the sum that go to an activation function to produce the output. And basically, all neural networks have that as their core, let's say, elements. And the goal of quantization, as it was explained previously, is to transform the way all those values are coded, most of the time on 32-bit floating numbers, into something much smaller, usually 8-bit integers. So we have seen in previous presentation that the gain is very significant. It can be divided by 4 quite frequently, actually, and the gain is impressive with a very limited impact on accuracy loss. So there are several ways to quantize, and it's important to have that in mind. Our target will be a traditional CPU on this ARM A72, but if you think about other applications for the future, you also need to consider possibly GPUs on tensor processing unit, CPUs, and you can do post-training dynamic quantization. By using, you don't need any data requirement, which is very an important factor when you choose a method for quantizing. You can do that statically. You just need here unlabeled representative samples to do that properly. And when you want to involve the quantization deeply into the processing, the learning process, you will need labeled training data. So this is clearly a constraint when you want to retrain your method. And in most cases, you can get significant reduction in size. And depending on which method you use, you can either target or not TPUs in particular, which can be useful in some applications. So to give a bit more information about what it means, dynamic quantization is about, let's say, keeping some flexibility at the activation function in the neural network. You have the activation function f as a reminder. So it is dynamically that the 32-bit mode would be activated or not, or switch back to 8-bit integers to save size. So here there would be a cost clearly at inference time, but it's a good trade-off usually to mix this dynamic mode with weights and the dynamic aspect on the activation. Sorry. Second approach is a post-training static quantization, where you would use a representative data set. Here, everything will be, let's say, reduced to 8-bit integers using the data set to measure the error and to do a proper quantization based on the data themselves. So that's simpler in a way, and it is probably the faster approach. And this is where you can deploy on more constrained targets like TPUs, where you have a fixed point accumulator somewhere, and here is very adapted to that. Quantization aware training, here it's the most sophisticated one, particularly adapted to convolution neural network. And here you would use the labeled dataset to integrate directly the quantization during the processing and the learning process. And that will lead to the best result, usually a bit more costly at training time, but probably the best result. Decision tree here is proposed to choose the best method. The key factor is, are you able to retrain the model with labeled data? If yes, you move probably to the quantization aware training. If not, if you have just a representative data set with no label, you can use it to post training dynamic quantization, or go fully static if you want maximum speed. And you can still do statically a mix between 16-bit and 8-bit integers to have a good mix as well. So, or have everything, last case, in 8-bit. So this decision tree is very useful to choose which best method is the best, and you can experiment around this. The good news is that it is directly available in your favorite TensorFlow library in particular, or others. A very simple example coming from the tutorial here. It's on the left, it's a construction of a traditional neural network using the MNIST dataset for character recognition, a very famous example. And on the right, you just have to convert your model to TensorFlow Lite, and it's a few lines of code to write, and you perform the quantization in a third step. Here again, very simply, here it's the default quantization to dynamic range quantization. So it's a dynamic, let's say, quantization on the activation. And it is very simple to do. In a few lines of code, very reliable and simple to read. You can save at least half of the memory needed for your neural network by just adding a few lines of code. So this is highly interesting. Okay, a few words have been said already on the pruning. I will not spend too much time on this one, but yes, there is this famous publication that was published, I think it was 2015. And the idea is to try to remove synapses or pruning some neurons directly, remove them, and integrate that into the training, a bit like we can do quantization aware training. It is a similar principle where you iterate and try the best approach, and the savings, the improvement can be really huge. So here again, it's available in most, in many, let's say, deep learning frameworks. So it's quite accessible, and you don't have to recode all that by hand. Another approach, which might not be so appealing at first sight, but it is very useful to sometimes consider more traditional machine learning techniques. Forget about deep learning for a minute, and you can consider a Gaussian mixture model or support vector machine and see how they perform. It's in any case, it's always a very interesting experiment. It's very easy to implement as well with scikit-learn, for example. Recent publication continue to have an interest into that, and it is highly interesting in very constrained environment. We have seen the ARM72 processor, but we also have older generation FPGAs, which can only store a few parameters, and it is where it is of high interest to just store, for example, the parameter of your Gaussian mixture model, which are basically mean and standard deviation for each component or each dimension. It is very simple to store and manipulate. It has a good advantage of simplifying the software stack. You have little dependency, you don't need any GPU, etc., to train, for example, things. So it has quite a few advantages, and not to be excluded at first level, let's say. And it can bring very, let's say, acceptable performance in plenty of cases, as it is explained. It is this recent paper, which is from November 2021. Okay, a few words about the portability aspect. We know that there are plenty of deep learning frameworks, TensorFlow, PyTorch, and plenty of others. In general, it's good to have some portability, being able to move from one to the other, and especially be able to target some specific runtimes. There is a very interesting Apache project, TVM, Tensor Virtual Machine, which is active for a few years now. It's coming from University of Washington, and there is a company now behind to support this. Very interesting project with quite advanced capabilities, and it can target especially our ARM A72 processor. So the principle is to have a intermediate representation of all the tensor operations, high-level differentiator functions, for example, and there is a kind of compiler in between that produces the right code to target the right hardware target you want. For example, it can be a GPU, C code, or a DSP, for example. Okay. The performance that are exposed, at least on this benchmark, we are investigating this library to fully validate it and to see how good it can be on the long run. But the first results that are exposed here for this specific processor, which is on board the ISS, are quite impressive, and it performs really well compared to other runtimes, ONNX and TF Lite in particular. So to be confirmed on our applications, but yes, quite interesting, and the principle behind are in any case of very high interest. Okay, we are getting close to the end of the presentation, but before concluding, yes, I would like to say a few words about scheduling. In software engineering in general, it's very frequent that your application is scheduled at some point in time, and it will be the case here with Imagine E. The different applications that will be selected will be scheduled with a scheduler. The Microsoft Space SDK that will be used for this offers very nice scheduling capabilities, and it is an opportunity for you as an application designer to think about it. How can I better handle my application by handling error management, so that the scheduler, for example, can retry. Maybe it can be a way to parallelize the applications to control in a better way the resource usage. So think about those lines. It's always a good practice in software development, and it is particularly valid in that case, knowing there will be a scheduler. The details will be refined once the application will be selected. For example, the max duration parameter will have to be set at an appropriate level, so that the application will have enough time to do what they need to do. It will not be hours, of course, probably, but maybe a few minutes, something like this, to be refined. But clearly, this will be a topic at some point, and think along this to design your app. Okay, now it's time for a few takeaways. So Imagine is a fantastic test bed. It's a huge progress compared to what we had a few years ago. Hyperspectral and RGB camera. We insist a lot on that, but the learnings that will be, let's say, taken from the hyperspectral activities on applications in particular will be useful for future mission. We are thinking about Chime in particular, which is currently being designed. The hardware is quite powerful and versatile, and it is a very flexible processor, but probably not the best processor in the world for deep learning application on inference, but still good enough if we use proper optimization techniques that we have described: quantization, pruning. We can do that with usual deep learning frameworks, and maybe it could be good also to consider more traditional approach if they work well enough and with very small hardware footprints. That it's always good to take. Keep in mind the scheduling, that's important to have a good execution and smooth execution for the application. And keep in mind also the portability for the future. It's always good to explore those possibilities. And there is clearly an explosion of hardware possibilities in the edge computing world. Same for software capabilities. So keeping in mind the portability is always a good practice. And that would be it for the conclusion. Thank you very much for the opportunity to present and your attention. Thank you.
Thank you very much, Nicolas. So I think with this last presentation, we arrived to our last item on the agenda for today, which is our Q&A session. I know that already some of you asked quite a few questions through the Q&A function of the webinar, and we already answered to you. However, we also wanted to have a few minutes because, yeah, we still have time until, let's say, 18:30, so 10 minutes, let's say, we want to keep in case you have any other questions. So exactly as I said, tell us if you have some specific questions for our speakers or for the challenge in general, how it is, let's say, undertaken, and about the next steps. So maybe while we are waiting for our participants to type their questions using the Q&A answer, maybe just one question, and I think this one is directed to you, Nicola. So maybe just I will read out loud the question, and we can answer it. So just as before, the training during Imagine takes place on the ground. So onboarding is not training, it's only deployment. Is that correct, or can you provide more details on that, Nicola?
Yeah, basically it's correct. And the goal clearly, I confirm, is to train your algorithm on your infrastructure, either in the cloud or somewhere else. And indeed, the goal is to produce the machine learning models and then bundle it into your application and then push that so that it can be uploaded to the ISS. Yes. So
Okay.
basically, yeah, you can still imagine, let's say, for example, incremental learning or things like this on board directly. It's a possibility, clearly, but on the baseline, I would say yes, it's correct.
Okay, perfect. Good. Then let's see if we have further questions. Okay, so we just got one in. So I will read the first one. So I'm still interested in knowing if Sophia's team faced any challenges when trying to convert to TF. So was the training done in PyTorch and the simple conversion using export was done, or a little more methodology was applied? Sophia?
Yes, I can answer. So yeah, the training was done on the basis of the model PyTorch, and then we just did a direct conversion to TensorFlow 1.
Okay, good. Thank you very much. Then let me go through the next question.
I don't
yeah.
know if Alessandro.
Yeah, sure.
If I may also integrate what Sophia was saying. So we also in the set-to-map content have tried to work with PyTorch, and we really support the recommendation from ISA to work with TensorFlow because it will speed up and the integration.
Got it. Thank you very much. Good. Then maybe let's just wait until we receive some other questions. In any case, if maybe some questions don't come exactly on this moment, we are going to make available this webinar, so you can watch it on your own time and maybe, let's say, focus on certain parts that you wanted more explanations. And obviously, we are always available either on the hello@ai4eo.eu for further questions, or you can also use the forum functionality on the platform where we have all the information for both tracks. Okay. So, okay, I just received a very quick question for the Imagine E track. So a participant is asking if they can use PyTorch for the Imagine E track. Is there any restriction, Nicola?
I don't think so. Basically, yeah, we have started to test a few things with it, and I think that should be fine. Yes.
Okay. Good. In any case, please don't forget that let's say the first phase of this challenge is for you to try to be, let's say, as ambitious and also as creative as possible. with your solutions. And then once we, let's say, have a look at your solution and see the potential of it, we are going to, let's say, fix all these little details on how your application can actually run on the satellites. So I would suggest right now to try to be as ambitious as possible and creative. And then if you're successful, we'll figure it out, all the small details. Okay, we have another question also for the Imagine track. So someone is asking if there are any model size limits in terms of memory for their applications, I presume.
So on the model itself, I would say no, but you have to keep in mind the memory limit, the minimum memory limit, which is 2 gigabytes. If I am not wrong, let me come back to the slide. It's on. It's 8 gigabytes, sorry, for the memory, and for the storage is 2 gigabytes. So if you need to store statically your model, it will have to fit in 2 gigabytes plus other things for your application, of course. So this is basically the rules. And if you want to load it in memory, same approach, make sure that it fits into 8 gigabytes, and that should be okay. I guess that you will have several models. So if each of them is 1 or 200 megabytes, that can be quite quick, and so be careful. But there is no explicit limit on the model size. Yes.
Okay.
Is that clear? Yeah.
Okay. Good. We also have another question, but it's not exactly related to today's topic. But just for you to know, yes, we'll let's say display the results in the upcoming days. So I reckon tomorrow, or at the latest the day after tomorrow, you'll see your scores for milestone 2. Good. Okay. Then maybe let's just allocate another 1 last minute to see if someone has some last question. And if not, we'll conclude with this webinar, and let's say we'll enjoy the rest of our day and the rest of this week. Okay. Then again, maybe as the last advice, exactly as I said, we are going to post the recording of this webinar on our YouTube channel. So we'll send a newsletter when that recording is going to be live, and you can rewatch it. And again, exactly as I said, if you have any further questions, we are going to be available either on the forum functionality, so on the platform AI for EO challenges, or you can write us directly on hello@aa4eo.eu. Also there, we are trying to get back to you in a maximum of 48 hours upon your receiving your email. Good. So with this last information, I think it's my pleasure to thank all the speakers that let's say made this webinar possible, sharing all their insights about what you should consider for your AI model and what you should consider for your prototype for this challenge. Again, also thank to you, the people that participated to this webinar, for your questions, and I would say for all the people that are involved, both, let's say, the consortium of FISAT2, ESA, and obviously the people behind Imagine, so Thales Alenia Space and Microsoft. We are very much looking forward to your solutions, to see what you are trying to do, and what, let's say, maybe new applications you are proposing. So exactly as I said earlier, try to be as imaginative and as creative as possible, and then we'll figure it out, the details in the later stage. So once again, enjoy the rest of your day. Thank you very much for attending our webinar, and the best of luck with your solutions. Bye-bye.
Goodbye, everyone. Bye.
Bye.
Now,
Thank
thank
you.
you.
Bye.
Bye.
Thank
Bye.
you.
Thanks.